Hello, good morning, everybody, and welcome to Papalim Physics Classroom. Okay, today we will be going through one past year paper for pure sciences. Okay, the code is 6091. Okay, before we start, okay, just to update everybody. Okay, remember for this video, I'll be going through the paper 2 from the first question to the last question. So if you happen to have the paper and you want to go through only a certain questions, right, particular questions, you just skip to that portion. Okay, so no need to listen all the way through. Okay, so and same as before, if you need the paper, I will leave it in my Google Drive, which is in the description link below. Okay, feel free to go and download and try out the paper. It's actually a very good paper. Okay, and if you have any questions, just drop me a comment. Okay, hopefully I can try to assist you. Okay, without delaying, okay, let's start. Okay, with the first. Now for paper 2. Okay, now for paper 2, the interesting question here I actually highlighted in the question paper here. So these 5 questions are actually quite interesting. Okay. So let's take a look at this. Now, for the question one is on kinematics. Okay, question 1 on kinematics. Okay, the kinematics is talking about parachutists. Okay, jumping from the airplane. After that, up for aircraft. After that, then then the parachutists open the parachute. Okay. Now, so what happened in this particular case is you are given the speed time graph. Okay, the speed time graph, okay, is at various section A, B, C, yeah. So A, B, C, D, E. So now let's look at the part A. Describe the velocity of the parachutists at A and C, between point A to point C. Now we are given a velocity time graph. Okay, so take note, for velocity time graph, if I need to describe the velocity, okay, the velocity time graph, okay, the idea that every time we see questions like describing the action or describing the motion, okay, for the velocity time graph, I always tell students to bear in mind that actually the answer they are looking out for is actually the acceleration, okay, of the, okay, when we're looking at the velocity time graph. So if the question gives you displacement time graph, okay, and they ask you to describe, okay, what you're looking for is actually the velocity of that the graph itself. So if you put displacement time graph, velocity time graph, and acceleration time graph, they are linked in such that whenever I'm looking at displacement graph and I need you to describe, I actually need information about the velocity, the next additional information. So if the question give you velocity time graph and they ask you to describe the motion, okay, from using the velocity time graph, actually what the question wants is actually he wants information about the acceleration. Okay, so what you're looking here is that every time the graph, whenever the questions ask us to describe the motion using the kinematics graph, the answers is always like additional level up. So displacement time graph means I need information about the velocity, one level up. If I need velocity, if I give you velocity time graph, I will need one level up. Okay, I will need information about the acceleration. So basically what they are trying to tell is I need the accelerations, okay, between point A to C, which consists of point A to B, then after that point B to C. Okay, so these are the two sections that are point A to point B actually has two patterns. Okay, meaning the gradient of the graph actually, or the gradient of the graph is constant. And at this junction here, as it approaches B, the gradient is actually decreasing. Okay, so gradient of the acceleration of the BT graph give you the acceleration. So which indirectly will actually give you an answer. So for example, let's say for this, I will actually look at the velocity. Because it's a constant gradient, it means that it's actually a constant acceleration for A and B. Starts with, okay, constant acceleration. Then after that, the acceleration start to decrease. Okay, the gradient start getting gentler and gentler. So, and later the acceleration decreases. Okay, so that's what we mean by describing the graph. I need information about the acceleration. Then in this case, same thing. Okay, how about part B and C? We are looking at B and C. We are looking at the fact that it is horizontal. Okay, horizontal here gradient is 0. Okay, so gradient is 0. It means that the acceleration at this point in time is actually traveling at maximum speed, 0 acceleration, or aka what we call terminal velocity, with, okay, 0 acceleration, which implies is traveling at maximum velocity. This maximum velocity is what we mean by where it's a constant value, and we have a term for it, and this term is what we call terminal velocity. Now, so for part A, so this is it. Okay, Now, for part B, okay, he says the part B has one additional constraint, which means the question says using feature in part figure 1.1. So what feature are we looking at? If I'm looking for acceleration, the feature that I'm using it for the graph will be actually the gradient. So this is what I'm looking for, what I'm using the feature, okay, the gradient of the velocity time graph here. For A to C, it goes two sections. So it's A to B, then followed by A to C. Okay, now, okay, for A to B, for the first part of A to B, it consists of this part, first portion of A to B, which is a constant gradient. So from the graph, I actually know that it's actually from a constant gradient. This is the beginning of the portion. And what does constant gradient tell me? Constant gradient actually tell me that the object is moving at, okay, is having a constant acceleration. Okay, so acceleration and force, what's the link between them? That's whereby that's your famous Newton's law, which is F net equal to ma. So when you have a constant acceleration, given that mass is remain the same, right? The resultant force acting on the parachutist will actually be the same. So the first part that we are looking at is actually constant acceleration. So which will imply that the resultant force acting on it, on the parachutist, okay, is actually constant. So that's first information about the resultant force we're acting on the parachutist at the first portion of AB. Now, at the second portion of AB, okay, you'll find that second portion of AB, this is the portion that we are looking at. This portion, okay, this portion of AB, the gradient is getting gentler and gentler. So at this portion here, okay, the gradient is actually decreasing. It's getting gentler and gentler. So which means we can say that the gradient is actually decreasing. And when the gradient is decreasing, it also implies, like in the previous question, the acceleration is actually decreasing. And when acceleration decreasing based on Newton's law, you'll find that the resultant force acting on the parachutist at the second portion of the motion for AB is actually also decreasing. Okay, so you'll find that as the parachutist jump, okay, as you go through the motion in the sky, as it's dropping down from the sky, you'll find that the resultant force actually acting on the parachutist is actually getting smaller and smaller and smaller, and eventually at point BC, you'll find that at BC, because the gradient is a straight line. Take a look, this straight line here that we are looking at, this straight line. Okay, the gradient is constant, I said 0. So we at this portion here, the gradient of the graph is 0. It will imply the acceleration is also 0, and F resultant force, and the resultant force based on Newton's law, the resultant force will also be 0. Okay, so this is how the information from the graph in figure 1.1 actually aid us in finding out what is the resultant force and how we do it. Part C, now what happened to the drag force on the parachutist? Okay, so let's say now we take a look at the parachutist. Let's say the parachutist is dropping down, okay, in this way. Okay, so this is the parachute. So the person is dropping down. Okay, this is the acceleration. Now, while the person is in the air, okay, weight is acting on the object, and there is what we call the drag force. Okay, so the drag force is at the back. Based on Newton's law, you'll find that the resultant force F net is actually equal to the weight minus away the F drag. Okay, because they are in opposite direction. That's the resultant force acting on the object. And for point C, okay, at point C, we already know that at point C, that is where the parachutist actually open up. This is the position whereby the parachutist will open up the parachute. So the moment I have a parachute, what will actually happen here? Okay, when I open the parachute, okay, when the parachute is open, okay, the moment the parachute is open, you'll find that this parachute, when it open, so big, okay, the parachute open, the drag force actually increase by a lot because you have a bigger surface area. Okay, and since weight is constant, this is constant, okay, you'll find that the resultant force acting on this person here is actually getting smaller and smaller. So that's how the whole situation works. Okay, now for point CE, now at point CE, what happens is CE is after your parachute is open already. Okay, so when your parachute is open, so what actually happens is that when the parachute is open, the force acting on the parachutist will actually be, the resultant force will be actually be decreasing. Resultant force decreases. Okay, you'll find that the acceleration of the parachutist is also decreasing. Okay, and when the parachutist is decreasing, you'll find that the drag force or the speed of the parachutist will also be decreasing. So in this case here, where after the parachute is open, you'll find that the motion of the speed of the parachutist dropping down is actually slowing down. So when the speed of the object, the speed of the parachutist is decreasing, you'll find that the drag force will also be decreasing in this case. Okay, so as the drag force decreases, you'll find that the whole cycle will repeat again. Okay, so whole cycle will repeat, whereby the resultant force will decrease, okay, acceleration will decrease, velocity will decrease, and the drag force will decrease. And eventually, what will actually happen is that the drop in the drag force will be equal or will balance with the weight of the parachutist. And when this happens, you'll find that, okay, the acceleration of the object will resultant force acting on the parachutist is actually 0. In this case, the acceleration is 0. And when you have 0, you will mean that the parachutist will be operating or be dropping at a maximum velocity. But just that in this case, because of all the decrease in acceleration, all the decrease in speed, you'll find that this parachutist now is actually traveling or dropping down to the object at the slower speed here. Okay, so that's why as the object, as the parachutist drop down from C to E, you'll find that at E, after everything stabilizes, okay, when it reaches terminal velocity again, okay, this terminal velocity is actually smaller than position C, okay, before the parachute was open, okay, because of the drag force. So now let's look at question 2. Okay, for question 2, in this case, is an energy question. In this case, we are looking at the object block, okay, which is released from point P. Release, on the keyword that I like to highlight is the word release. It means the velocity is actually 0 here. Okay. Now, what actually happens is for energy question, I always like to look at location by location. For location P, okay, the energy that we are talking about is actually the potential energy. So there's only potential energy here at the beginning. And after a drop, it goes through the track and eventually it lands at point Q just before entering the rough surface. So at point Q here, okay, since it's at the lowest point, you'll find that the energy we are looking at here is only kinetic energy. So all the energy will actually be transferred already. For question A, I need to find the speed at Q. Okay, so if I will look at it, I will just calculate the speed at Q. I will just use simple conservation of energy for position at P and Q. Okay, because the total energy, okay, the total energy at P will be equal to the total energy at Q. What energy are we looking at? At P, I only have potential energy. At Q, I will only have kinetic energy. So here what we do, I will substitute in all the formulas. Okay, and I should be able to get the answer right straight away actually. So EP potential energy is mgh. Kinetic energy is half mv squared. Okay, the mass can cancel one. Okay, just take note. Okay. So it will end up, if we rearrange the term, it will be v squared equal to 2gh. Okay, so v will be square root 2gh, which is times 1. Okay, and this answer, if you work out answer, it will happen to be, let's take a look, it will be 4.5 meter per second. Okay, so this is the answer. Okay, I would say it's quite easily done. Now for part B, okay, it's after the object went through the rough surface, there is a spring, it compressed by 2.2 meter or 20 cm, and energy stored is 4.5. So at S, based on the question at S, okay, the energy I'm looking out for here is elastic potential energy. So this is elastic energy, okay, at the end of the stage here. Okay, now from Q to S, okay, I think if I know I need that, okay, I need energy overcome the rough surface is QR, is 36 joules. So now from Q to R or Q to S, okay, so from Q to S, what is the conversion that we are looking at? Okay, you'll find that from Q to S, the total initial energy at Q, okay, the total energy at Q will be equal to the total energy at S, Q. When the object go from Q to S, he actually go past this rough surface. So there is actually work done. Okay, so there's any losses in terms of the friction, so it will be work done across the rough surfaces. Okay, so this is work done by the friction. So in terms of conversion of energy, okay, the energy from the initial stage to the final stage, it actually comprises of the energy at S plus the friction at work done due to friction, the loss of energy due to friction when the object passes through the surfaces. So when we look at the initial energy, there's only one energy, which is the kinetic energy at Q before entering. After entering, you'll find that the energy you are looking at is the total energy. After I pass through cross surface and end up on the spring, the energy converter will be the spring energy, which is 4.5 joules, plus the energy I need for the friction. And EQ, you actually found already. EQ is actually half mv squared, or what we call mgh, which is the answer here. Okay, so if I submit the value, I will actually be able to replace this number with half m 4.5 squared. Okay, so if you substitute all the equation, you'll find that the answer you work out, it will be a nicely work done by friction. Okay, so you rearrange the values. Okay, half mv squared minus 4.5, you'll find that the answer will be just correct, will be 36 joules. Okay, so just take note of the energy conversion equations. Remember, at this particular point from Q to S, there is an additional energy, what we know as the heat loss, okay, due to all the work done to overcome the friction. Then, of course, part C will tell you calculate the friction. Okay, so there's a simple substitution formula. Work done is force times distance traveled. The energy need to overcome the friction is 36 joules. Friction, no, I don't know. That's what I'm supposed to find. Multiply by the distance traveled. The distance traveled based on the question is 2 meters. So this is 2 meters. So if I rearrange, I will know that my average friction force will actually be 18 Newton. Okay, so this is the answer that we are looking at. Okay, so quite easily done. Okay, now question 3. Question 3 is a kinetic model. Okay, so now the first question is why is the pressure is the same at all points? Okay, so what happened is, first thing, of course, kinetic model. Okay, how does pressure exerted? We look at the molecule itself first. So which means that you must tell the marker that you can write continuous random motion, okay, by the particle. And so what happens does this random particle, what does this random motion do? He will actually exert the force, okay? You exert the force, and not just any force, you actually exert the force at different directions, okay? Because it's random, so all the direction at the location is actually randomized one. So you exert a force any direction, any angles, any magnitudes, okay? So everything is really by random, any direction or in any magnitudes, okay? So what happens is, so the average force per unit area is actually constant. And this will mean that the pressure will also be constant at all points. Okay, because of the first thing is because of the randomized motion of the object, the force are randomized, directions are randomized, and as a result, the average force of everything, okay, per unit area will be constant. And this is how we explain the pressure exerted on all points of the inner wall is actually constant. Okay, now for the second part, what happened? Why does the pressure decreases as the size of the balloon increases? Okay, first, now we need to understand first. Okay, when the balloon go up, okay, when the balloon rises, okay, I would say the pressure of the balloon and the pressure of the atmosphere. So what happened in this scenario is as the balloon go up. So here, let's say as the balloons went up, you will find that there's less air molecules around, and as a result, the atmospheric pressure will be actually decreasing. Okay, so the atmospheric pressure will be decreasing. Okay, and in this case, right, when it decreases, okay, you'll find that as of now, the balloon pressure is still the same. But because the outside has actually reduces, now my outside pressure there has actually reduced, which means that my internal pressure, okay, now is actually higher than the exterior pressure. Okay, so this is what happened at this part. It happens together, but it actually it can be broken down into different stages. So then what happened is the exterior, now pressure in the balloon, okay, is actually higher than atmospheric pressure. Okay, so now what happened is when the balloon is higher than the atmospheric pressure, there is actually a difference in pressure. And this difference in pressure will actually cause a force to be exerted on the balloon to push the balloon outwards. Okay, difference in pressure arises, then it will cause a force to exert on the balloon, pushing it outwards. Why outwards? Because pressure always goes from high to low. So now my interior pressure, the pressure of the balloon is higher. So as a result, it will be pushed outward. So it will push outward from the interior to the exterior. So now my balloon actually get bigger. Okay, so this is what happened. The balloon actually get bigger. Okay, so now, but this is not the end yet. This only explained to us, right, that the balloon size increases, but it has not explained to us what happened to the pressure inside the balloons. Okay, so now we come to the next stage now. Okay, so at the next stage, what happened now is this. As the balloon become bigger, okay, the balloon become bigger, there's more space for the molecules to move. Okay, but the molecule is still moving at the same speed. So what it does is, remember, as the balloon become bigger, the collision inside the balloon actually becomes smaller. So because it is getting less and collision is less and less often. So which means the collision inside the balloon decreases. Okay, so the frequency of collision actually decreases. Okay, because now the balloon is getting bigger and the speed doesn't change. The speed is still the same. The space now is bigger. So you actually collide with the wall, collide with each other, actually a much lesser frequency. Okay, decreases. And what happened? The average force exerted per unit area decreases. Okay, because now the average force decreases. And since we are talking about average force per unit area, this will lead us to what we know as the pressure inside the balloon decreases. Okay, so for 3 marks, I would say it is that there's quite a lot of things to write. Okay, but of course, the good thing is that this particular set of answers is actually quite standardized. Now, for question 4, we're looking what is the specific latent heat of fusion. So which means I need to know the MLF for this particular stage. Now, you'll find that the question given is that they uses the same heater. Imply, okay, it's the same power. Okay, the same power that's used. The power at both sides, power at heating is actually equal to the power at melting. Melting is actually the second stage, which is the green color one. They are same power because why? They are the same heater. Okay, so for heating phase, the formula will be the energy needed will be MC solid delta theta. Okay, that's the formula. But we are looking at power, so we must divide by time. Okay, so for melting, which is the green stage, which is the melting stage, the green color horizontal line, the formula we are looking at will be MLF. But same thing, we must divide by time because power. Okay, so this is for melting. So this is for heating. Okay, so now with this, okay, we do a simple manipulation. The M and M can cancel. Then after that, we look at the formula inside. So LF, if I rearrange the formula, it will be CS delta theta Tm divided by TH. Okay, so now let's look at the substitution. Okay, LF, so I'll just write this here. LF equal. Now, CS is given already. So where is CS? The question we have already, this is your CS. Okay, so it will be 1.6 times 10 to the power 3. Delta theta, change in temperature for heating, is always high temperature minus low temperature. So negative 210 is considered high temperature, negative 220 is low temperature. So it will be negative 210 minus negative 220. Then what is Tm? Based on the question, Tm is the temperature needed to melt. Tm temperature needed to melt is 400 and 160. So the time difference will be 400 minus 160. Temperature for heating will be quite straightforward, 0 to 160. So it will be just 160 seconds. So once you have all the number, you punch your calculator, you will get the answer, a nice number. It will be 2.4 times 10 to the power of 4 joules per kg. So this will be the latent heat of fusion for the nitrogen. Okay, so just take, so it will be the answer, quite easily done. A bit tedious, but still quite manageable. Now, then after that, same thing. What's the heat capacity for liquid nitrogen? Okay, the approach will be the same. Okay, the approach that we are looking at, it will be using the heat capacity, whereby now we look at the power, because they are the same heater. It will be the same thing heater. Okay, so now same thing for melting. But now, whatever energy I need for melting, okay, what the power that I use to melt the heater will be actually the same as the energy I need to heat up the liquid nitrogen, which is at the third phase here. So this is the way I heat up. So this one would be, I would say this is the power needed to heat the liquid nitrogen. Okay. Okay, so this will be mLF divided by time taken to melt. Power to heat up the liquid, it was same formula, mass of the liquid. Okay, heat capacity of the liquid now, plus the temperature needed to heat up the liquid, divided by time taken to heat up the liquids. Okay, here just take note, the heating up, now we are looking at the pink color phase. We are looking at the pink color phase. So if we are looking at the time, okay, it will be 600 and 400. So let's say now if I substitute the equations, same thing. Let me do a bit of cancellation. The mass is the same, so I will cancel the mass. Okay, nothing much. Then this is where I shift the working. So CL. So now we find CL, you do a bit of manipulations. Okay, I mean to get CL, I need to cross time TL, heating of the liquid up. So the final equations will look like LF THL divided by delta theta and TM. So now with this, okay, now we substitute all the variables inside. LF, you found already. LF is on top. Okay, LF is this particular branch. LF, you found already. This is the answer. So I substitute inside. 2.4 times 10 to the power 4. THL, time to heat up the liquid, which is 400 to 600. So it will be 600 minus 400 seconds. Delta theta, same thing, high temperature minus low temperature. So high temperature is negative 200, low temperature is minus negative 210. So it will be negative 200 minus negative 210 multiplied by the temperature to melt, which is 400 to 160. You'll find that the answer here will be 2 times 10 to the power 3 joules per kg per Kelvin. Okay, that should be the answer. Okay, so just take note of it. Now, the next question will be your lenses. Lenses, I would say, this question is quite straightforward. Okay, so if it's a standard lens question whereby the drawing is here. I would say the only trick here that you must be careful is when the question, as in this question, you need to literally use a ruler and measure. Okay, because this is like a graphical approach. Okay, so this drawing will include the three ray diagrams. So the three rays that you use. So I will not dwell too much on this question 5 because I would say it's quite a standard question. Okay, so if you have any problem regarding light rays, okay, refer back to my videos on light rays on getting the lenses, especially on lenses using the three ray diagrams. Where I will upload the link in the URL here. So if you need, you can just click on it and just actually refer to the video there. Okay. Now for question 6. Question 6 is, I would say, is a bit of like data analysis whereby you need to analyze the question. Thus, I explain why sounds first travel along, how sound arrive, okay, along data at path 2. Okay, or why sound arrive faster at path 2. Okay, remember path 2 is Earth. Earth means solids. Okay, so which means the idea here, the common question that we see is actually what compare the speed of sound in solid versus in air. Okay, because we need to know, okay, as in you have to know that it's in air and solid is in the solids. Okay, the particles are closely packed. Okay, the particles are more closely packed. Particles are more closely packed than gas, which is air. Okay, and because of that, you'll find that the passing of speed is actually much faster. So which means when I pass, it actually created a series of rarefaction and compression. So to pass, okay, I need to have, there will be a series of rarefaction and compression, okay, being set up. But the difference between the particle in solid being closer together and the setting out the rarefaction and compression, with these two factors, you'll find that, okay, the speeds of the molecules, okay, the speed of the transfer of the transmission of sound in solid molecule is actually faster because the particles are closely together, and when they form the rarefaction compression, the closeness of the particle actually helps in transferring, okay, at a faster rate. So as a result, the speed of sound in solids, okay, is actually faster than gas. So this will be the answer that we are looking for. And so in task, he will actually travel at a shorter time. Now with this in mind, same thing, we look at question part B, is that the speed of sound in air, remember it's in air. Okay, the distance between the detector and the sound. So standard thing, I would say this is the classic example of constant speed. Okay, it will be distance divided by time. Okay, so distance, it will be speed times time. And remember the speed given is 320. Must remember the time that we are looking at, this time is, I'm looking at path 1, not looking at path 2, because path 2 is on Earth. Okay, so path 1 is on air. So for this particular object, because the question say, oh, I want the speed, I given you the speed of sound in air. So 320 refer to air. So the path taken for the air will be 0.01. Okay, so this will be 0.01. So the distance, it will be 32 meter. Okay, state 1 assumption made, you make in calculation of B. This one I would say is a quite standard thing. You can say that the speed remain the same. Okay, speed is constant throughout. If not, you can say that there's no energy loss. Okay, no heat loss. Okay, because when you transmit, sometimes there will be collisions and there will be heat loss. So now we say there's no energy losses during the transfer. Okay, if you don't want, you can look at if you don't want, you can use based on the question about the spacing on the molecules. The spacing of molecules remain the same, or what we know as the density of the gas molecule actually the same. So any three of these three answers will actually be more than enough. Okay, these two are actually the most common one. Okay, hence calculate the speed of sound in Earth. Okay, same thing in Earth. Okay, in Earth, if you know this distance is 32 meter. Okay, if you know this is 32 meter, and you know that the speed on Earth is 0.2 seconds. Okay, so I would say a simple speed is distance divided by time. You know the distance is 32 meter. The time is 0.02 seconds. 0.02. 0.02 seconds. If you punch the calculator, you will find that the answer will be 16,000. Okay, so that's the speed of the sound in Earth. Okay, last question. Okay, explain why the sound travel faster or slower in the layer of travel faster or slower in the layer of rocks than it does in Earth. Now the question look at the layer of rock. So where is the layer of rock? Okay, you go back to the picture, you'll find that the layer of rock is here. Okay, so now when you look at layer of rock, we're actually looking at path 4. Okay, the path 4 here. So this is the path 4 that we are looking at. At the layer of rock surfaces, the path bend away from normal. Okay, the path bend away from normal. So which means instead of going straight like this, instead of going straight this way, it bend away from normal. Okay, and when I bend away from normal, what does it mean? When I bend away from normal, it means that it actually means that the speed of the particle is actually faster. Okay, so this will imply that the speed of the sound wave actually, okay, in rock is actually faster. And this is how I look at how I deduce from the question here. Because from the question, I know that, okay, they are traveling away faster and the path bend away from normal. And because the path bend away from normal, I can deduce that the speed of sound is actually faster in your solid here, okay, in the rock. Okay, that's how we are able to look at the questions. Now let's look at question 7 here. Okay, question 7, right? You'll find that actually it's a classic example. It's a quite common example where we use polyethane sphere. Normally, if we have a polyethane sphere, okay, it's quite obvious it's always an insulator. Okay, so which means if you're looking at for electrostatic, so insulator means the charges cannot move. But what's interesting about this question is that the setter actually coated it with a layer of silver paint. And what's so fantastic about this move is that once it's coated with silver paint, the new polyethane sphere with the silver paint actually becomes a conductor. Okay, so this is the trick that students need to identify. Okay, normally polyethane sphere is a conductor, insulator, but now because I'm coated with a silver paint, the polyethane sphere is actually a conductor. So it behaves like it has a similar behavior like a metal sphere. Okay, and like what all metal sphere look at is when you have a positive rod, okay, brought near to the system, brought near to the sphere, what will happen is the charge are actually free to redistribute themselves, okay, such that, example, positive rod, I got charges here. So when I redistribute the charges for my polyethane sphere, which is a conductor, I will have actually negative charge on the left side, positive charge on the right side. Okay, because why? Because your light charge in conductors, your electrons charges, negative charges are free to move around. Okay, so this was will settle for the answer for part 1, 7A part 1. Okay, so just take note, the idea is you must realize that the coated sphere is actually a conductor now. Now, with the aid of diagram, explain what happened when the rod is actually brought near to the sphere. Brought near to the sphere. Okay, brought near. I would say we can actually break down into different stages. So now at the beginning now is when it is far away. Okay, so at stage 1, okay, I would say is at when the rod and the metal rod and the sphere are like side by side. Okay, they are like beside each other yet, or they're near each other. Okay, at this point in time, you'll find that the attraction force between positive charge rods and the electrons. These electrons are referred to the left-hand side of the sphere. Okay, so we are talking about this side and the left side of the electrons. So this area here, you have a attraction force, and this attraction force you will find that it's actually stronger. Stronger than what? Stronger than the repulsion force. Okay, stronger than the repulsion force between the positive charge on the right hand side and the positive charge on the rods. So this is what happened. Okay, it's stronger. Okay, then the repulsion force between the positive charges, rods, and the positive charges. Okay, so likewise, the positive charges here are referred to the right hand side. So in this case, why? Because you need to understand that the between the positive and negative. Okay, so this is the blue color highlighted one. Okay, just to be I color code it. Okay, the attraction force are between the positive and negative charge. The opposite charge is actually stronger. Why? Because they are actually nearer to each other as compared to the positive charges. So that's why your attraction force is actually stronger. So what happens is, because it's stronger, you'll find that this will lead rise to your stage 2, which means it will lead rise to your rod moving towards each other. Okay, so at stage 2, which is at stage 1, what's the end of stage 1? It means that the rods, or to be exact, is the sphere. The sphere will be attracted to the rod itself. Okay, so which means what you're looking at stage 1, the rods, okay, and the sphere, because of the location, because of the charges, you'll find that the sphere will actually move towards the rod himself. Okay, so as the rod and as the negative charge and positive charge rod and the negative side get closer and closer, the attraction force is actually getting stronger and stronger. Okay, so now this is what happened to the particular stages here. So when stage 1, you find that the positive charge, the attraction force will be stronger than the repulsion force. And what happened is at stage 2 now, okay, stage 2, after you're attracted. Okay, so after you're attracted, okay, what will happen? Okay, the sphere and the rod will touch each other. Okay, so the rod is positive charge. When the sphere touches the rods, okay, remember, as sphere touches the rod, what happened? Okay, you have a positive charge on the left side, negative charge on the right side. So what you do is, at this moment in time, what we know as neutralization will actually take place. Why? Because the electrons, or the negative charges on the sphere, remember, on the sphere, will move to the rod itself. Okay, so when they touch, okay, you'll find that the rods, the negative charge here will actually move over to the rods. And what will happen when the negative charge move over, plus, minus, they will meet each other. Okay, and what happened? Okay, the negative charge, okay, will be neutralized. Okay, so when it is neutralized, means inside the sphere itself. At this moment in stage 2, after the electrons has been neutralized, after the electrons has moved over, the sphere, okay, will only be left with positive charges. Okay, because the electrons has been neutralized. So what is left over is only the positive charges. Okay, so now what happens is, now when you have positive charge, okay, so when you have positive charge on the right, okay, so your positive charge sphere is on the right, and you have a positive charge rod on the left. Okay, so when they touch, so what happens is, now you have what we know as your light charge light charges will repel. Okay, the rod and the sphere will actually move apart. Okay, the rods and the sphere, okay, will actually move away, repel from each other. Okay, so this is what happened to the whole cycle there, is that when at the beginning you have a positive charge, you have a positive charge rod move over, you move nearer to the sphere, which is a conductor. Okay, you'll find that the sphere will actually be attracted to the rods because unlike charges attract at this moment in time. Then when they physically touch, okay, you'll find that the electrons from the metal sphere will actually move over, will be transferred over to the positive rod. And when it transfer, okay, the positive charge will actually be neutralized. Okay. And so when it neutralize, what will happen? Okay. And the negative will be neutralized, or will neutralize. Let's say I want to neutralize. We'll neutralize the positive charges. Okay. The positive charges on the rods. Okay. And when it neutralize, okay, you'll find that you only left with positive charge on the sphere only. And of course the rod will be positive charge also. So now you have two positive charge, and what will happen? You'll find that they will repel against each other. Okay, and after that, the rod will actually move away. Okay, and so this is what happened to the whole cycle. Okay, now at part 2, now if the sphere is not coated with silver paint, so here, like I mentioned before, if it's not coated with silver paint, when it's not coated with silver paint, there's no silver paint, your sphere, polyethane sphere, okay, he will remain as an insulator. And insulator, like we all know, you cannot charge by induction, okay, because the charges cannot move. Okay, and thus what happened will remain uncharged. It doesn't allow the electron to move. So now for 7C, okay, now what happens is if I have the same experiment again, but now the rod is actually earth. Then after that, here is the important thing. I remember the sequence. I remove the wire first and the earth wire. Okay, I move the wire, which is the earth wire. Then after I remove the positive charge rod. Now, originally what happened is you have positive charge here. Okay, so you will have negative, negative, negative on the left side, positive, positive, positive on the right side. So to neutralize means that the electrons will actually move from the earth wire down to the atom here. Okay, and as a result, okay, remember after that the wire is being removed. Okay, so after it's removed, you only deal with electrons. Okay, and the best thing is after the wire is removed, the positive charge is also removed. So after you touch it with the metal paint, okay, so you earth it with wire now. So you are left with negative charge on the rods, and as a result, a negative charge on the sphere. Okay, so when the sphere is still here, okay, you'll find that the electron distribution is still by the left hand side, because why? Unlike charge attracts. But then when I remove, okay, when the wire and the positive charge rod is removed, you'll find that, okay, the space, okay, is actually, there's no more attraction, so which means the electrons will actually be repelled towards furthest corner away to balance out all the charges. Okay, so what we call evenly distributed. Okay, so take note of this. So the answer that I'm looking at is actually this. Okay, so draw the charges on the sphere after everything has been removed is 1, 2, 3. Okay, so it's balanced out the thing. So evenly distributed, remember. So remember the wire. All right, for question 8 here, question 8 is a transformer, but now instead of 1, you have 2 okay, 2 transformer, X and Y. Now let's take a look at this question. Now the power generator, which is on the left side, it produces a current of 10 amp, and the voltage across it is actually 400 volts. Okay, so I will say this is the primary side of the transformer X. Okay, then the total voltage supplied by transformer X is actually 48 kilovolts. Okay, so power line, so which means this side is actually 48 kilovolts. Okay, current not sure yet. Total resistance of the power line is 200 given here. Okay, it's not ideal cable. Okay, then after the voltage supplied by transformer Y to the home. Okay, transformer Y to the home. So this is the voltage we are looking at, is 240. So which means this voltage is actually 240. Okay, so this is what we mean by the information that is given to us. Okay, so ideal transformer, both are ideal transformer. So ideal transformer, what does this statement mean? Okay, students, you need to be aware of this. Okay, ideal transformer, take note, when you have ideal transformer, okay, ideal transformer, actually the one of the common thing that we have is actually power at the primary is actually equal to power at the secondary. Important information that we need to know about the ideal transformer. Okay, now what is the power supplied by the power station generator? I think this one is very straightforward. Power in circuit is controlled by IV. So power generator is the primary coil of X, PX, let's say primary coil of X. So I will have the current in primary coil X and the voltage of primary coil X. Okay, so both of them I have the number. Current is 10 amp, voltage at primary coil is actually 400 volts. So the answer I have is actually 4,000 volts. 4,000 watts. Okay, so this is the answer. Now, calculate the current flow in the power line. Okay, power line, where's the power line? The power line is here. Okay, when looking at the power line, okay, the power line is here. Okay, when we say current flow in the power line, it means this. This is the current in the power line. But current in the power line in this case is also actually current of the secondary current of X. Okay, so what actually happened is the question is indirectly asking you to calculate the current in the secondary coil for transformer X. Okay, you can use the formula IS, okay, equal to IP equal to VP over VS. Okay, remember the transformer formula. You are given VP, you are given VS, you are given IP. So IS is actually VP. What's the voltage in primary coil, which is 400 volts. Okay, secondary coil is 48 kilovolt, which is 30 here. Okay, multiply by the current in primary coil. So this will be multiplied by 10. Oh, sorry, this will be multiplied by 10. Okay, then you'll find that IS is actually, this should be 0.083. Okay, so that's one way of looking at it. Then after that, hence or otherwise calculate the power loss in the cable. Power loss in the cable is actually referring to the resistor here. It's actually referring to the resistor, which is 200 ohm. So basically, power in the resistor will be controlled by P. Power loss is actually equal to I square R. 0.083 squared times 200. Answer will be 1.37, or I would say 1.38 watts. There's a power loss. Now, of course, what is the turn ratio of transformer X? Remember, for X, we are looking at is this. You are looking at turn ratio is NS over MP. Okay, so it can be solved by finding NS over MP, or you can find VP over VS or IP over IS. Okay, so now take a look. Okay, so if I want NS over MP, I can actually use VP and VS because VS is given 48 kilovolt divided by, here will be, remember, turn ratio, leave it as a fraction, 120. So the turn ratio here will be actually 120. Okay, so this is how you look at it in terms of the formula for turn ratio. Remember, turn ratio, the common booby trap is you must remember S over P, but this is P over S. Okay, so you must know what formula are you looking at. Now, both transformer X and Y are removed, and the power station is now connected directly to home, where the generator is here. Okay, so I'll connect directly to the home. Okay, so what is the voltage that is set up is 400 volts and 240 volts. Okay, so now if I connect, it's not connected directly to home. So which means if I connect directly to home, the home need 240 volts. So which means I can no longer transmit at high voltages now. I cannot transmit at 48 kilovolts. So what I do is I have to transmit, if I connect directly, I have to transmit at 240 volts. Okay, so what happens is if I transmit at 240 volts, now is, remember, if generator transmit low voltages, okay, in primary coil, okay, when you transmit low voltages, you'll find that, okay, you will transmit low voltages, okay, to the home. You transmit at low voltages, which means that if you transmit at low voltages, he must transmit at high current. Okay, so generator transmit low voltage, it means the current transmitted, okay, this current we are looking at, this current here, okay, is actually very high. Now, then after that, what happens is if it's transmitted at very high at this junction here, okay, and since, what does high current means? Okay, the current transmitted will be very high. What does this mean? It's because your heating effect is P equal to I square R. So if your current is high, you'll find that the power in the resistor here, okay, the power, okay, loss will be high. Okay, so when your power cable loss is high, less power reaches the house. So actually most of the house, most of the energy transmitted, majority of the actually lost is actually lost during your transmission. You need maybe example like you transmit 100%, but maybe 80% is actually wasted as heat loss, and only 20% reaches the component, other families. Because if you transmit at low voltages, the current that you are transmitting is actually very high. And when high current you transmit, the power loss in the cable because of the formula I square R can actually be quite high, okay, which is a bad thing because it will catch fire or this. Okay, so this is one of the things that we have to be very careful. That's why I purposely, or the people around it purposely built 2 transformers rather than just laying one cable connect from station to home. Okay, they will rather go through the power station, because if I go through power station, the voltage is high, the current is low, the heat loss will actually be much lower. So actually I can put more power, more energy to better use instead of being heat loss to the environment. Okay, now let's look at question 9. Question 9 is a data analysis question. Okay, so in the sense that there will be information given and students will need to read carefully. Yeah, so in this case, we are looking at the mass selector. So now let's look at the question. Okay, now the important thing about here is the picture itself. Okay, after reading the information, okay, the story, you will find that there is actually 2 forces in play here. One would be the electric field, electric force. Okay, this force actually arises because of your plate here. There's a 2 plate, parallel plate. One is negative, one is positive. The other one that we're looking at is your magnetic field. Okay, magnetic force, sorry. Your magnetic force, it arises because there is a magnetic field in this region. Okay, coupled by the fact that this is a positive charge. So there will be a force induced on these particular charges. Okay, so now let's take a look at the different forces. Okay, so now for question 1 is you are supposed to identify the electric field, electric force, and the magnetic force. Okay, so look at the magnetic force first. Now, for the magnetic force, since this is a positive charge, this is negative charge, so this will be unlike charge attract, so the force will be upward. Same thing as just double check on the bottom plate. This is positive charge. This is positive charge, so you have unlike charges. You have like charge repel, so it similarly will be upwards. So you'll find that the forces due to the 2 plates is all in the same direction, which will give us a conclusion that the electric field, okay, by both plates will actually amount to an upward force, or upward force, what we call Fe. So this is the electric field here. Now, if you look at the the magnetic force, you'll find that the important thing about magnetic force is when you have your Fleming left-hand rule. Okay, Fleming left-hand rule, if you look at the video, the picture here, okay, you'll find that the force field current, the index finger is your current. Okay, so that's one important thing. The index finger is your current. Based on the question, it is actually pointing out of the paper. Okay, so if you look at if you prepare your left-hand rule, okay, you pointing out of the paper, and the current is actually going to the right. Okay, because you must take note of this, is that your current direction, okay, the current direction, okay, is the same direction as a proton direction. Okay, because they have the same behavior. Okay, then compared to their current direction, if you compare it to an electron, the negative charge, okay, the direction is actually opposite to the electron's direction. So this one, students, you have to be careful. Okay, so if the question give you an electron or proton, so you must know which direction your middle finger will be pointing it. So in this case, based on the paper, the charge is moving to the right. Okay, the charge is moving to the right. It's a positive charge. It will mean that your index finger, your middle finger, which is the current, should also be pointing to the right, same direction as the current. Okay, positive charge and electrons, positive charge and current should be the same direction. So if you use a Fleming left-hand rule, you'll find that the magnetic force on the electric charge, on the positive charge, will be actually be downwards. Okay, so this will be a magnetic force. Okay, one up and one down. Okay, explain why, in terms of forces, why the positive charge actually remains at its position, or so-called emerge undeviated. In terms of forces here, based on the question in part 1, the forces we are looking at is actually Fe and Fm. Okay, I would say this is quite straightforward, because one look you will know that the force for him to travel undeviated means go straight to the right, from left to right. It will mean that the forces are actually the overall forces on the object is actually a net zero forces. Okay, so this is what happened, is that from here you are able to deduce that the Fe, the electric field, actually balance, okay, with the magnetic field, magnetic force. or what we known as Fe equal to Fm. Okay, so when you have this condition, if you look at your Newton's law, you will find that the net force, okay, applying on the positive charge will actually be 0. Okay, why? Because F nets equal MA. Okay, in this case, your F net will be Fe minus Fm. So since they are the same number, it will be a 0 on the right side. Okay, so since if your net force is 0, what will happen? Net force 0 doesn't, you still have not answered the question completely, because if the net force, it still doesn't account for why the charged particle emerge undeviated. So you need one more line, one more keywords that we're looking at. So when its net force is 0, it will mean that the acceleration of the object, okay, will also be 0. So when the acceleration of the object is 0, it will mean that your Newton's first law was set in, meaning the object previously, whatever motion he has previously, okay, will still continue in his original path of motion using the same speed. So, or what we know as he will travel, okay, at a constant speed, okay, in the same direction. And this is what I mean by what the question means by undeviated. Okay, so this is what we mean by 2 marks question. Okay, so that's why I think there's a reason why they give you 4 lines, so you write a bit more. Now, so what happened now is this. Okay, so I will draw the charges here. So now the positive charge is here. So on top, you will have an electric force. Then you balance out by the magnetic force. Okay, so this is the charges. So what will happen for part 3 is that what will happen if less electric charge and less positive charge on part P1 and P2. In this case, the first statement here will tell you that if you have less charges, okay, on the plate itself, okay, straight away you will know that the electric field, actually the electric force will actually be reduced. And in this case, once the electric field force is reduced, you will find that the electric force now is actually smaller than the magnetic force. And in this case, or what we call the downward force, is actually stronger than the upward force. And what will happen? There will be a net force which is pointing towards downwards. So within there will be a net force. Okay, there will be a net force acting. Okay, there will be a net force acting on the object. Okay, a net force acting on the positive charge and that direction. Okay, pushing the charge. Okay, net force downwards, so pushing it downwards. Okay, so this is what the question, what the students need to understand. Because now we are looking at 2 forces in play. Okay, so one is stronger, the top is weaker now, the bottom forces, which is the magnetic force, is stronger. So overall net force, there will be a downward force. Now is the reverse. What happened will be the magnetic force is reduced. In this case, now the magnetic force is reduced, which means that the magnetic force with the reducing magnetic field, the magnetic force actually will be reduced. So it will be the same answer as part 1, number 1, whereby now the only difference is the direction is different. Example, now because the magnetic force is reduced, so the electric force is actually bigger than magnetic force. Net force acting on an object in the upward direction. Okay, so as a result, he will actually curve, deflect upwards, or he will actually curve towards the maybe diagonally top right corner. Okay, so this is the idea is the same. Now, 1 and 2 is quite similar, but just it affects different forces. Now, slightly interesting will be number 3. Okay, number 3 will look at that the charge is actually negative. The field line is still in the same direction. So only the charges is reverse. Okay, as I mentioned before, right, your current direction and the current direction is always opposite, okay, to electrons. Okay, to your electron direction. So this one you must remember. So the moment I reverse the charges, when I change the charges from positive to a negative charge, is aka the current direction also reverse. So once the current direction is reversed, you will find that the magnetic force that produced now, okay, the magnetic force produced, okay, will be different, okay, or might change. So you need to examine the thing again. So now with this question here, let's refer upwards for a picture for clearer view. So now let's say let me erase this. Okay. So the same electric field, same magnetic field. So now what happens is if my charges here is, let's say, let me clear it first. So now let's say this is negative. Okay, I have a negative charge. Now the electric field is still the same. So now for electric field, this is negative, this is negative. Light charge, it will repel. Okay, and this is positive, this is negative. So unlike charge will attract. So which means for electric field, for P1 plate and P2 plate, top plate and bottom plate, the force is actually acting downwards. Where the electric force is actually acting downwards. Okay, due to the attraction and repulsion for a different plate, but they are in the same direction. Same thing now is we are looking at electrons. So the direction will be different. So if you look at your magnetic forces, if you use a Fleming left-hand rule, okay, your field is still coming out of the index finger, the field is still coming out of the paper. Okay, then after that, your current now, although the charge is going to the right, but it's the electron charge. So which means your current is in opposite direction, which means your middle finger should actually point to the left. Okay, so now what happened is you'll find that the magnetic force will actually be pointing down. Your magnetic force will actually be pointing downwards. Okay, so now for this case, if you use electrons, okay, with the same magnetic field line, the same electric plates, P1 and P2, you'll find that now the forces acting on the electron is both downwards. FM and FE is both pointing downwards. So you'll find that in this case, you'll find that the FE, okay, and FM, okay, are both pointing downwards. So you're pointing downwards. Okay, so both are pointing downward. And what happened? Okay, and as a result, your net force, same as the previous one. So you're looking at the net force on the charges, okay, will be a downward force, will be downwards also. Okay, causing the deflection. Okay, to be downwards too. Okay, so this is what I mean by the answer. Okay, so the keywords that we're looking at is you have to highlight to the marker about the changes in the electric field and the magnetic force, and the sum of the interaction between these two forces. What does it result to? It results to a net force, which is also pointing downwards. Okay, so this one you must take note of it, because a lot of students, I think they make the mistake to say that they make the assumption that, oh, if I negative charge, right, if I change it to a negative charge, oh, only the magnetic force changes. Okay, because now it's opposite. Just now it's positive, now it's negative. So the positive charges actually, the magnetic force changes. But then they forgot to account for or to check the electric field. Okay, whether the electric field has impact, okay, on the negative charges, what happened to the electric force. Okay, so students, you have to take note of this small hiccup that you might make. So just be careful of what you are looking at. Now for part B, you have this selection process. Under this selection process, there are different paths. And one of the important, and among the information that's given to you other than the path, is actually the ratio. The important thing is this ratio, because you will need it later on. The ratio is that the radius, the curvature, the radius is proportional to what we call the mass to charge ratio. Okay, so this is important. Now, based on information, there are different particles A, B, C. Okay, the charges is positive, -1, negative charge, positive charge, and +2 charge. Now, based on the information, okay, now state the path traced by particle C. Particle C, okay, particle C here, you know, is a positive charge. Okay, but it's a heavy positive charge, which is 2 + 2. Okay, so now is the positive charge. Let's look at whether the path is left or right. Important thing, if we need to take note, is the field is pointing outwards. So which means if you use a Fleming left-hand rule, your index finger should be pointing upwards, out of the paper. Okay, and the beam is going downwards. Okay, so the beam is going downwards. Okay, your positive charge down means your middle finger should actually be pointing downwards. Okay, so out of the paper, pointing downwards. Okay, out of the paper means the magnetic field is out of paper. The index finger should be pointing up or out of the paper. Your current should be, okay, pointing into the field line. Okay, or downwards. Okay, towards you. You let go of your thumb, you'll find that your thumb will point to the left-hand side. So which means the positive charge particle C will follow either W or X. Now, how do you know W or X? Okay. Now, where W or X is in terms of the radius itself. Okay, so you look at these two radius, right? You will find that if you do a comparison between 39 particle B and particle C. So let's say if they are both positive charge. So which means that one of them will be path W, one of them will be path X. Okay, so now which path are we looking at? So you will find that since they are both positive charge, okay, so in the sense that because both of them are positive charge, they'll be either, they'll deflect to the left. Okay, deflect to the left. But left, there are two paths, W and X. So how do I know which particle will do W and X? That's whereby this information, radius, okay, is important. Based on the information, right, the radius is actually controlled or dependent on two things, the mass and the charge himself. Based on the question, right, you'll find that actually the two mass, B and C, the mass is actually quite close together. Okay. But what happened is that the force himself, the charge itself is double. Okay, B and C, the difference is that the charge is double, which means the denominator is actually twice. C is, in terms of denominator, the C is actually double of B. So you'll find that if I'm looking at radius of B, radius of C, okay, because my charge of C, charge of B, okay, my charge of B is actually smaller, okay, at least by half a times, or to be exact, C is double of B. You will find that because of this information, of this factor, which is charge happen to be double, C happen to be double the charge of B, and charge happen to be denominator of that formula, you will find that it will affect the radius. So if my denominator is bigger, my radius actually will be smaller. And since my charge C is double, it will mean that, okay, the radius of C will actually be smaller than B. Okay, so this is what we mean by using the information to help you assist in your in your answering. So which means that your charge C, particle C, will actually follow, okay, the shorter path, okay, or path, the curvature, the path with the shorter curvature, which is path W. Okay, so that's why I can conclude that the path that I will choose is actually W. Okay, and how do I know? Because if I want to explain, because of this factor, okay, because my charge is actually less than Q, my C is actually double of that, and because of that, you will find that, okay, the radius of B is actually bigger than radius of C, based on the formula, okay, R is equal to Km over Q. Okay, so this is the three things that students have to tell the marker. One, okay, to make this is what I mean by making use of the information given. Two, followed by three. Okay, so once you are able to tell the marker based on the information that you select, so you have to use the information given in the question, formulas, data, and even the pictures, to conclude that the path is actually W. Once you are able to done this, you'll find that the force will be actually the answer is actually quite easily done. Okay, but one thing to caution you is this. Okay, the key thing here rests on the fact that you must be able to identify that it is using your left hand rule that it is on the W and X. If your left hand rule doesn't, if you make mistake in your left hand rule, you find that the whole question will mess up already. So it's left hand rule, right hand rule, Fleming left hand, Fleming right hand, and Maxwell right hand is very, very important. It's very useful. It's utilized quite a lot. For question 10, I would say it's a classic example of your Faraday and Lenz law, but just that instead of those circular coil, now I give you a rectangular coil. Explain why there's induced current, okay, at 10.1, okay, and determine the direction of the current himself. Okay, now as coil enter, okay, the field, the magnetic field. Okay, let me use short form first. Magnetic field lines, magnetic field. Okay, there is actually a increase in magnetic field lines. The field line will actually be increasing. Okay, and what happened is the coil will actually detect, okay, will experience a rate of change of magnetic field lines. Okay, and after you must highlight to the marker is that what happened is this rate of change, it will cause the EMF to induce on the coil itself. So you will find that the EMF will be induced on the coil. So if you look at Faraday, there are three things that I will tell students they must write. And the third thing that we look at is to highlight to the student, highlight to the marker that the size, the magnitude of EMF induced is proportional to the rate of change of magnetic field lines. Okay, so these are the three things that I always tell students. Or if you write Faraday, these are the three things that you must always write to show to the marker that you actually understand what is. So these are the keywords that we are looking at: rate of change of magnetic field lines, induced, and is proportional to the rate of change of magnetic field lines. So what happened to the induced current? Now, based on your understanding of Lenz's law, you will produce the current. The current will flow. The induced current will flow such that it will oppose the motion. So which means that on paper here, right, you'll find that the field line is out of the paper and it's actually increasing. So in this coil, the field line is actually increasing. So to oppose the motion, the field line must be in opposite direction. So which means the field line that is generated by the induced current must oppose the motion. So if the field line experience is out of the paper, increasing, so getting stronger and stronger. So the induced current will actually make sure that it will be opposing, which means if his field line is coming up, his field line will be going in, likewise increasing to match the change. Okay, so this is what I mean by action and reaction. Lenz's law look at action and reaction. So if the field line is increasing, okay, out of the paper and increasing, okay, so for example, if I write out, it will be more obvious. So which means the field line experience, the field line experience will be out of the paper, okay, and it's actually increasing. So by Lenz's law, the induced current or the induced magnetic field line, the induced pole, okay, the induced magnetic field lines must be opposite. So it means it must be inwards, okay, it must be going into the paper, and it must also be increasing, okay, to match the change, okay, opposite, okay, to oppose the changes. So which means your induced field line, okay, is always going into the paper in this case, and is always increasing, okay, and as a result, you'll find that for using a Maxwell rule, for field line to be increasing means your thumb is pointing inwards to the paper, and you turn your right arm, your fingers on your right hand, you'll find that the current is actually flowing in the clockwise direction, this way. Okay, so in this way, it will be your current, your induced current will flow in this particular direction. Okay, so what happened here now, you have to write it out in words. So for Lenz's law, I will always start off with since the circuit is closed, okay, the induced current will flow clockwise. Okay, if you don't want to write clockwise, you can write the direction like P, Q, R, S also can. Okay, so we flow in the induced clockwise, okay, to produce a field line, to produce a magnetic field lines, okay, to oppose the change. Okay, so okay, if you don't want to write change, you can write the rate of change of magnetic field line, also, flux linkage also can. Okay, and this will be the complete answer. So if you look at the the Lenz's law, usually it will encompass two parts. The student must be able to usually I will start with to tell the marker that it's a closed circuit, and also to tell the direction of the induced current, and to also to produce a magnetic field line that will oppose the change of the rate of change of magnetic field line, the word oppose. Okay, so this one is I say the usual three things that I write for Lenz's law. A part 2 now. Now A part 2 talk about asking the student to see what is the induced current, okay, in figure 10.2. Now figure 10.2 to take note is that the coil is already inside the magnetic field line. So which means, right, within this area, as long as the coil PQRS is within this area, okay, all this area, as long as the coil is within the area, what pattern or one phenomenon that you see is that while the coil is inside the magnetic field line, you'll find that the number of field lines, the amount of field lines inside the coil is always maximum. Okay, so maximum magnetic field line. So whether the magnetic coil is moving to the left hand side, from left to right or left center right, you'll find that the amount of magnetic field line inside the coil is always maximum. So which means whether I move from position 1 here, or I move to position 2 here, okay, the amount of field line is the same. So which means one of the things that student must take note is that while the coil is in the field line, okay, while the coil is inside the magnetic field, okay, at 10.2 there's always maximum change, there's always the maximum field line, but there is no rate of change of magnetic field lines, okay, during 10.2. No rate of change meaning, right, the number of fuel line inside the coil always remain the same. There's no changes, but it's always maximum, 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 maximum. So what's the change? The change is 0. Okay, so then remember for Faraday, when you look at induced EMF, right, we are looking at the rate of change of magnetic field line. It's not the amount of fuel line inside, it's how much the fuel line changes. So if there's no changes, there's no rate of change of magnetic field lines. Okay, this will mean that there is 0 EMF induced in the coil. So that's why we can safely say that when the coil is in figure 10.2, or to be exact, is while the coil is inside the magnetic field line, all the coil, when the whole coil is inside, okay, the whole coil is inside the magnetic field line, okay, you will find that there is no rate of change of magnetic field lines, and therefore it is 0. Okay, so this is what we mean by 10.2. Now, the 10.3, part 3 will be the reverse. What happened when at figure 10.3? 10.3, you look at the picture up there, is whereby the coil PQRS actually exit the magnetic field line. The extra thing that the question asks is that other than we need to tell the marker how do we know what happened to the coil, and we also need to know how to determine how do I determine the direction of the induced coil. So other than knowing how to do, I also need to tell the marker how am I going to determine the field lines. Okay, now while exiting, okay, this is exiting. So which means while exit, right, students, you have to take note that while exiting, okay, so between this guy is exiting, so this is exiting, so this is empty. Okay, so empty means what? Empty means, right, just now previously at 10.2, the field lines inside the coil, totally all the coil PQRS is maximum field line. But now while PQRS is exiting, the number of field lines inside the coil here is actually decreasing. Okay, so which means just now is maximum, now is decreasing. So now there is a rate of change of magnetic field lines. Okay, so if the field line is decreasing now, okay, the field line entering the coil is decreasing, based on Lenz's law, okay, your induced current will actually flow in a direction to reverse or to oppose these changes. So if now I know that my field line is actually decreasing, so the induced current, what you do, it will oppose the motion. So it will make sure that the field line must increase. Okay, so between the field line, he must try to increase the field line. So between the field line, we'll actually try to boost the decrement. Okay, we'll try to slow down the decrease. So which means the field line will actually be in the same direction as the magnetic field line on the paper, which is outwards. Okay, the original field line is outward of the paper. So to the coil now, the number of field lines entering the coil is getting lesser and lesser. So what the induced current will do, they will move in such a way that they induce their own current, their own magnetic field line will actually produce a magnetic field line that will actually counteract the decrement. It will actually make it increase, okay, or slow down the decrement. So between this field line must be out of the paper, same direction as the original field lines, the field lines that is pointing out of the paper. Okay, to oppose the changes, to prevent it from dropping, to prevent the field line in the coil from dropping. So what you do, that if I know the field line is out, okay, so which means if I use a grip rule, Maxwell right hand grip rule, okay, my thumb should point out of the paper. So which means the induced current actually should flow this way. This is where the induced current should flow. In this way, so if you look at your Maxwell right hand grip rule, you will find that my grip rule, my field line, the induced current must actually flow in the anti-clockwise direction, so that the field line will actually reduce the reductions. Okay, so this is what you need to tell the marker. Okay, making use of Faraday and Lenz's law. Okay, so let's put all this thing in words. So now let's take a look. Let's see. Okay, so now, okay, so as of now, the coil will experience a rate of change of magnetic field lines, or magnetic flux linkage, or magnetic field line, okay, as it leaves the coil. Okay, so now what you do is that so there is a rate of change of magnetic field line, so which means at this point there will be an induced EMF. So there will be an induced EMF. Okay, there will be induced EMF at the coil. This is Faraday. So after that, you will bring in Lenz's law and grip rule. Okay, because the Lenz's law will account for the induced current direction. What is the direction? And you need Maxwell grip rule to actually determine the direction of the current itself. Okay, so now what happened is, Once I finish the Faraday, I will settle for the Lenz's law. Remember, Lenz's law, one of the keywords that I mentioned in part 1, okay, is that there are 3 things that I always want to write. So which means I'll write as the coil is closed or the circuit is closed, there will be actually induced current flowing. Okay, the induced current will flow, okay, to oppose the motion, okay, or the action. And what's the action? The action is that the fact that the field lines is actually decreasing. So you oppose it. So he will prevent it from decreasing. So he will try to increase it. Okay, he will try to boost it. Okay, so this is what we mean by your Lenz's law. Okay, so there is a induced current acting on the coil itself. So now what is the induced current direction? Okay, the induced current direction, okay, based on Maxwell right hand grid rule, the induced current must be anti-clockwise to produce a magnetic field that is coming out of the paper. This is what we mean by your Lenz's law. Lenz's law will state that, sorry, let's go back from the beginning. So if Faraday will state that the rate of change will have an EMF induced. Okay, Lenz's law will state that since the circuit is closed, the induced current will flow such that it will induce, okay, you oppose the action. So what action are we looking at? Okay, which is the fact that the field line is dropping. So what will happen is that the induced current will be actually flowing anti-clockwise, okay, to produce the magnetic field line that is coming out of the paper, which is opposing the changes. The changes is that the field line is dropping. Okay, how I determine the induced current in the coil for figure 10.3. Okay, I factor in, I use Faraday, I use Lenz's law, and I also use grid rule. Okay, these 3 laws always like work hand in hand. Okay, so you have to be good at these 3. Okay, now so let's look at what happened to the part B. Part B, you have a slip ring, you have an AC generator. So I will know that this is 1 cycle. So this is 1 cycle. Okay, so this 1 cycle, since this is time, this will be the period, will be 0.04 seconds. Okay, so now let's take a look. A change in the AC generator will show that the wave will be this way. So now for 1 cycle, okay, for 1 cycle, the period is 0.02 seconds. So now there's a change in cycle. And the other change that we take note is actually the maximum and minimum point. The wave actually become bigger. How do I determine the rotation speed? Okay, the rotation speed. Okay, when we talk about rotation speed actually determines how we affect. It will actually changes the frequency. It will actually changes the voltage maximum. Okay, the faster I turn, okay, the faster 1 cycle will be, or what we call the shorter the period it is. Okay, so let's look at how we are going to solve it. Okay, now remember the question here said figure 10.4. So don't use the wrong graph, use 10.5. 10.4, okay, is here. So for part 1, figure 10.4, the period we know is 0.04 seconds. And frequency is 1 over T. Okay, so if you know frequency is 1 over T, you will know that frequency will be 1 divided by 0.04. The answer will give you a nice number known as Hertz. Okay, 25 revolution per second, or what we call 25 Hertz. Now, state the time when the coil is parallel to the magnetic field lines. Okay, now here you must be careful. When the coil is parallel to the magnetic field line. In this question here, there are 2. If you see like some of the questions, there are 2 ways of asking it. Sometimes you're talking about the coil is perpendicular or the coil is parallel to the magnetic field line. Here, students, you must be careful. When we talk about let's say we have a magnet here, north to south. Okay, if the coil is perpendicular, meaning this is the field line, the coil is this way. The coil is perpendicular this way. Okay, in this case, right, you have noticed that when the coil is perpendicular to the magnetic field line, the force on the coil is actually in the same direction as the magnetic field line. Or to be exact, the force is actually parallel to the magnetic field line. So when the coil is perpendicular, okay, when the coil is perpendicular to the magnetic field line, this will mean that the force is actually parallel to the magnetic field lines. Which means if the field line and the magnetic field line is not perpendicular or parallel, your Fleming right hand rule will not be valid. So as a result, there will not be any EMF induced. So the EMF induced here will be 0. Okay, but on the other hand, if your magnetic field is this way, but your coil is actually parallel to the field line. Okay, in this case, when your coil is parallel to the field line, you'll find that your force is perpendicular to the field line. So in other words, if your coil is parallel to the magnetic fields, you'll find that the force is actually perpendicular to the magnetic field line. And in this case, your Fleming right-hand rule, okay, will be valid, and as a result, EMF induced will be the maximum, okay, and this is what we call your Emax, okay. So your location of your coil does matter, okay. Your location of the coil does affect the amount of EMF induced, and the rule of thumb that we're looking at is if your coil is parallel in this way, the EMF is induced is maximum. So based on 10.4, right, you will find that, okay, you'll find that when I'm looking at maximum, okay, when it's maximum, okay, when this is maximum, this point where voltage induced is maximum, it actually tell you the coil is actually parallel to the magnet itself. Okay, and when the coil is actually zero, when the EMF is zero, okay, this point will actually tell you the coil is actually perpendicular to the magnet itself, or what I mean by vertical. Okay, the coil is actually vertical. In this way, the coil is actually horizontal. Okay, so the different part of the voltage time graph will actually tell you the location of the coil himself. So if I want maximum, I want parallel here, it means horizontal. So it will have to be 0.1. Okay, it will be 0.1 or even 0.3. Okay, 0.01 or 0.03 seconds. Okay, so the time will be either 0.01 second or 0.03 seconds, whereby it is maximum. Okay, so position of the coil with respect to the EMF induced time graph. Okay, students, you must take note of what does the graph actually tell you regarding to the position. Now, with reference to 10.5 and 10.4, okay, what can you infer from the changes? 10.5, remember, 10.5, like I mentioned before, the only time whereby my frequency will change. Okay, my frequency change is whereby my speed of the thing increases, and when the speed of the turning increase, the magnitude will increase. So true enough, magnitude increase, the frequency actually changes. If you're not sure, you can calculate. So for 10.5, the frequency, the time is 0.02 second. It will mean frequency will be 1 over t. It will be 1 over 0.02. Okay, you know that the frequency here will be 50 hertz. So just now is 25 hertz. Now it's actually 50 hertz. So in fact, what actually happens is actually the frequency actually doubled. And when it's doubled, you'll find that the graph will actually be shorter, or what we know, the period will be shorter, or the frequency will be longer. Okay, so it depends on how you look at it. Now let's look at VA and VB. What is VA and VB? Okay, so if your frequency actually double at 10.5, your frequency actually double, my turning actually become faster. Okay, so which means that my magnitude of VA and VB, okay, VA, okay, and VB. So VB will actually be double of your VA. So which means 2 times of VA will actually be the voltage of VB. Okay, your VB actually double. Because what happens is because now your turning actually double. So the period actually getting shorter and shorter, or what you call the frequency getting longer and longer, or faster and faster, sorry. And other than that, because you are turning faster, the rate of change, the rate of cutting of magnetic field line is actually faster now. So with a faster rate of change, the EMF induced will definitely be larger. Okay, since your speed doubled, the EMF induced will be double. All right, okay, so let's look at 11 idle. 11 idle seems like a moment question. Yeah, I have the weight of based on the question, I have the weight of the rod here. Okay, weight of the rod, if it's a uniform, okay, uniform density, so which means it will be in the middle of the rods. Okay, so the distance here will automatically be halfway mark also. So this will be 0.3 meter. This will be 0.3 meter. So similarly, vertically, why? Because it's a uniform, it will be vertically, it will be also halfway mark. So this will be 0.5 meter. This will be 0.5 meter. Okay, so just take note of these hidden detail or those small details. Because your weight is in the middle of the stick. So because it is in the middle, based on similar triangle, you'll find that the horizontal and the vertical distance will actually be halfway mark for each of them. Now, by taking moment about the bottom of the stick, so let's say my pivot is here. So this is the pivot. Okay, so let's determine magnitude of n. Okay, so you only got two force only. So same thing, clockwise equal anti-clockwise. So they will be clockwise equal to anti-clockwise moment. So what are the clockwise moment here? Let's take a look. Clockwise moment as of now, you have weight only. With respect to the pivot P, okay, clockwise is by the weight himself. So this will be MW. Anti-clockwise as of now, the second force, anti-clockwise is N. Okay, and okay, so this will be anti-clockwise moment of N. So now let's take a look. Okay, force times distance. So the force for, let's say, for N will be force N. Distance for perpendicular distance of N, remember, perpendicular distance of N is always measured from the force down to the pivot. Okay, so this is the 1 meter that we're looking at. Okay, so the perpendicular distance for N is actually 1 meter. For MW, take note of it. MW is same thing. For moments, the perpendicular distance is always from the force himself measured to the pivot himself. Okay, the line of action, okay, which is the perpendicular distance, which is 0.3 meter. Okay, so the weight here will be, the weight is 8 Newton. So this will be 8 Newton. The distance will be 0.3. The N will be 2.4 Newton. That will be the answer. Now, part 2, okay, other than N and W, there's a third force acting on the stick by the ground. Okay, so one look, you'll know that there's a third force, so which means the ground is actually, there's a friction. So between the force will actually be this way. Okay, to prevent the stick from sliding down. Okay, so just take note of it. So as for the distance here, okay, the method here, usually you can either use tip to tail or you can use parallelogram method. Both will work. You can refer to my tip to tail or parallelogram method, okay, and just use it here so that you can solve the question. Okay, I will attach the video up in the link, in the link, so that you can access the parallelogram or the tip to tail method. Now for part B is a moment question again, but now it's a plank. Okay, uniform plank. Uniform plank. Okay, draw a free body diagram. Okay, of the wooden plank. Okay, stating the force on the plank clearly. So let's look at the plank. Okay, on the plank itself. Okay, on the plank, forces on the plank. Okay, forces on the plank. Confirm there is actually P and Q. Okay, force P is upwards. Okay, pulling the rod up, pulling the plank up. So this is F, Q, and FP. Then definitely you have the weight of the plank itself. Then followed by the weight of the person here. Okay, these are the 4 forces that's acting on the object here, on the plank here. Okay, now calculate the show the tension in P and Q to be 110. To find P and Q, we can use the first one. The easiest is to take moment. Okay, so now we have different forces here. So this is the person, weight of the man. So this is the weight of the plank. Okay, so there are 4 forces here. Okay, so this is P and Q. Let's say I want to take moments. Okay, so let's say we take moment about P. So which means I place the pivot at P. So the moment I place the pivot at P, okay, actually force P will not be considered in the moment equation because the perpendicular distance is actually 0 here. So here, same thing, clockwise equal to anti-clockwise. Okay, so based on the question with respect to P, now the pivot is P, you will find that, okay, the man will actually have a clockwise moment. The plank will actually have a clockwise moment. Okay, so these two will contribute for the clockwise moment. Okay, so the clockwise moment, there will be 2 of them. The moment of the man plus the moment of the plank. Okay, as for an anti-clockwise moment, it's actually by none other than the force at Q, by rope Q. Okay, so this is the anti-clockwise moment. So this will be the moment at Q. So essentially that for this, if I take moment of P, these are the 3 variables I have. So I will have actually the force, the rope on rope Q, plus the weight. Moment of the man will be the weight of the man multiplied by the perpendicular distance of the man. Okay, plus the weight of the plank times the perpendicular distance of the plank. So now is to substitute into the equation. For anti-clockwise, it will be force of Q multiplied by perpendicular distance of Q. Okay, remember my pivot is here. My pivot is at P. Okay, so for example, if my pivot is P, my perpendicular distance for Q will be from the pivot to the force himself. So this will actually be 2 meter because I know that the rod is actually 4 meter. Okay, so you substitute the number inside, it will be force Q times 2 meter. Okay, then weight of the person is 0.5, 800 Newton, 0.5 meter from P. So it will be 800 meter times 0.5. Weight of the plank is 1000 Newton. Okay, it is directly at the middle point. So it will be 2 meter, 2 meter. So which in fact, this will actually be okay, 1 meter. Okay, because weight is a uniform plank. Okay, the weight is at the 2 meter mark. So left hand side is 1 meter of P, right hand side will be 1 meter to make it up for a total of 2 meter. So it will be 1000 Newton, the weight of the plank, times 1 meter. Okay, so Q to be 700 Newton. Okay, so now let's take a look. Okay, so this is force P. Now for this pattern here, if you want to take, if you want to find Q, you take moment about P. So if I want to find P, I'll take moment about Q. So that's one way of doing it. So this one you can take a look. I can take moment about Q now, in order for me to find force, the tension or force of P. Or actually, I have another way, is I use Newton's second law, F net equal ma. Okay, because when you look at the plank here, because this plank is balanced, so which means all the forces actually will add up to be 0. Because this force is not moving, so which means I will actually know that if I use Newton's law, which is faster, you'll find that all the forces add up will actually be 0. Because the plank is actually not moving, or what we know as A equal to 0. Okay, so this is what, based on the question, is actually at equilibrium. Okay, so which means all the forces, the upward force and downward force, will actually be balanced. So which means Fp plus Fq should be minus weight of plank minus weight of the man should be equal to 0. So if you rearrange or you substitute all the numbers, get Fq, okay, to be 110 Newton. Easily done. So depends on this. For this, I would say that the first approach is always taking moment. The second approach is you can either take moment again, repeat the whole working again for Q. Okay, just now was P, now you take Q. Or you can actually use Newton's law to substitute to find the subsequent forces. So usually these are quite a standard mathematical approach. The plank move towards the center of the man move towards the center of the plank and eventually stop at the center. How does the tension in the rope and P change? Okay, now here remember, if the man move towards the center, one of the other forces remain the same. The one of the most obvious change here we are looking at is actually the perpendicular distance. The perpendicular distance of the man actually now increases. Okay, so from this, you can, from the first statement when I say I move towards the center, I can actually know that the perpendicular distance of the man to rope P increases. And because of that, you will find that my force P actually will decrease. And as I go towards Q, okay, if I get nearer towards Q, you will find that my perpendicular distance towards Q actually will decrease. So as a result, my force Q will actually increase. Okay, because the moment for the whole system must balance up. Let's say if you are still not sure of how I get the number, so you can take a look at a simple fact. You can refer to your mathematics for the working on top. Okay, now if I move towards the center, you'll find that my perpendicular distance, this area here, my perpendicular distance, okay, for this, okay, as the man moves towards the center, my perpendicular distance is actually increasing. So which means that this particular factor, okay, the moments by the man, as I move towards the center, the moment by the man is actually increasing. So which means that the right hand side of this equation will actually be increasing. The clockwise moment will actually be increasing because my perpendicular distance has increased as the man walk towards the center. So which means that for me to increase, to balance this, I must increase my anti-clockwise moment. I must increase so that I can balance the moments, because the ruler of the plank must be balanced. So for me to increase my anti-clockwise moment, okay, there's only two ways. Either I increase my perpendicular distance or I increase my force of the plank. But the distance between Q and P, this distance between Q and P, this distance is fixed. This distance is fixed. So based on the equation, you'll find that this is fixed. This is fixed. dq is fixed. So, but I need to increase my anti-clockwise moment. So if dq is fixed, the only way to increase my anti-clockwise moment is actually to increase my force q. Okay, and because of that, to maintain the anti-clockwise equal to clockwise moment, my FQ must increase, because by increasing FQ, I am able to increase my anti-clockwise moment, and because of that, I can actually balance the clockwise moments. Okay, so if you give the same treatment to Newton's law, okay, you will be able to deduce that FP will actually be decreasing. Okay, so this is how I look at it in terms of mathematically. Okay, or either you look at it through the common sense, the common sense, whereby when you shift to a center, based on common sense, you actually will know that which forces is actually increasing. Okay, but other than that, if common sense doesn't work, okay, it's not the end of the world. Okay, you can still rely on the mathematics, on the principle of moments to actually help you to deduce the answer here. Okay, so even for this 1 mark, one mark doesn't mean like the answer is like straightforward or it's just a 1-word answer. No, sometimes the 1 mark actually require a lot of 2 or 3 marks question. Okay, so just take note of it, students. Okay, for question 11, it's a circuit question. Okay, with light bulb. Okay, simple basic circuit. So no, I will not say simple. It's a basic circuit. Okay, now first question is, why is the light bulb A and B the same? Oh yeah, before we solve, one thing to caution students is that the questions actually identify that the light bulb are the same, identical light bulb. Okay, so question 1, okay, why are the brightness A and B the same? Now, before we rush in to say that the current is actually the same, okay, which is like the standard answer that we're looking at. Okay, before we look at, we need to look at brightness. Let's unpack brightness. When we look at brightness, we are not just saying that the voltage is actually the current or voltage. We are actually looking at one particular factor known as power. Okay, so which means in your answer, when we explain this answer, this 1 mark, it is not just saying that current same or not the same, what the voltage. It's not about current or voltage. It's actually about both of them. So your answer must actually include both current and voltage, because power is actually I times V. Okay, these 2 factors actually play a part. Okay, so now let's look at how we should phrase the answer. Brightness of light bulb. Why the brightness of light bulb is the same? Why? Partly because they are in series. In series, current, okay, flowing across A is actually the same. Okay, second point, what we are looking at is because they are identical light bulb. Okay, they have the same resistance, aka you mean that they will actually have the same potential difference. Okay, and since power is equal to I times V, the power and the brightness is actually the same. Okay, so look at what I have done. Okay, so I'm actually linking power with brightness. Okay, but it doesn't conclude brightness actually depending on volts or current. I actually look at both of them. Okay, so that's how I craft my answer to look at what are the keywords I need to write. So even for a simple 1 mark question, it doesn't mean that it's just a 1 mark or 1 keyword answer. Okay, 1 mark actually, it might require students to actually write a few sentences or a few keywords. So students, you need to know what are the concepts the teachers is actually testing, so that you can unpack that concept into the keywords needed. Now, a third bulb C is actually put here. Okay. Now, what happened to light bulb of B and C? Now, B and C, I would say, is quite straightforward because they are parallel and they have the same resistance. Okay, the moment they are parallel means the voltage across them, the voltage across VC and the voltage across VB, they are actually the same. And similarly, you must remember power is actually, what's the formula for power? It can be IV or it can be V squared over R, whichever is convenient. So by identifying the relevant factor, which is what? Now I would like to use V and R because it's easier, because I already know this factor already. Okay, so if I identify these factors, I can actually identify the brightness of the light bulb. Okay, since it's in parallel. Okay, so the first thing I look at is because they will have B and C, voltage of B will be the same as voltage of C. So these two will be the same voltage because they are in parallel. And secondly, because they are identical light bulb, it will mean that they will have the same resistance. Then once I have done this, I actually can conclude with it, because I know since power is actually V squared over R, power of both of them of B is actually the same as power of C. And this will lead us to conclude that they actually have the same brightness. Similarly, I unpack what I mean by power in terms of the relevant components V and R now. Then I compare V and R to get a satisfactory comparison on the brightness, or what I call the power of the lamp itself. Now, what happened to the brightness of A and B after connecting A and B? Okay, so when you look at A, you'll find that the current flowing through is here. After that, the current will split up. So in this case, since they are identical resistance, okay, you will find that the current, okay, you can look at voltage in power brightness in terms of this particular thing, or if one, you can take a third formula right here, I square R. So you can look at power in terms of any of the formulas here. Okay, so from here, you will see that, let's say if I want to unpack the brightness using, like I have done IV here, I have done V square over R. So let's say I want to unpack power, brightness, power. Then I look at it maybe in terms of, now I look at I square R. Okay, so now we look at I and square and R. Okay, so now based on the circuit, okay, I will know that number one, okay, all the light bulbs, okay, have the same resistance. Okay, number two. Now you'll find that if you look at the current at A, current at A, and current at B, because in fact that there is a parallel branch across B and C, which means the current, the moment he hit the node here, current IA hit the node here, current IA must actually split up into IB and IC. So which means, and the splitting is actually just nice, is exactly half, because both resistance B and light bulb B and C are actually the same. So in fact, I can actually conclude, right, that whatever current I have at I, half of the current will go to B and half of the current will go to C, because the resistance in both branches are identical. So which means just nice, the two branches, they will actually split. It will actually take the same amount, which happens to be half. So this is what I need to tell the marker. So which means here I will say, okay, the current through A, okay, IA will split, okay, into IB and IC, okay. And from this information, not good enough. This information splitting only tell me smaller, but I'm able to go one step further to tell the marker how small it is. And since, so you must tell that, and since, okay, resistance B is actually same as resistance C, light bulb B and C is the same, this will mean that IB, current in IB and current in IC will actually be the same. Okay, so if both current is the same, looking at math, I'm able to deduce that current of B is actually half of IA. So confirm B is smaller than A, not just by any, not just small, it's just half of it. And since, okay, and from there I can conclude that since power is I square R, if my resistance is the same, one of my current is smaller than the rest. Okay, if my current B is smaller than A, it will mean that, okay, power of B must be smaller than power of A. And from that, I will be able to deduce that the brightness of B, or bulb B, is actually lower than A. So actually the brightness of light bulb B actually has decreases. Okay, so this is what I mean by the concept that the setter is testing is about power. But it doesn't mean it's a simple formula. It doesn't mean the question is simple. It actually requires the students to unpack question number 1, 2, as in like part 1 and part 2, 1 and 2, 2. The marker expects the student to unpack what I mean by power relating to brightness based on his fundamental values, which is current, voltage, and resistance. Okay, so students, you need to understand how or why the marker is testing, or why the marker set this question, and try to empathize what they are trying to ask you. From there, you will be able to understand or elicit what are the concepts that is needed and what are the keywords that you need to give to the marker. So this is what I mean by writing the correct keywords in this particular aspects. Okay, now the part B and part 1, I would say is fairly simple. Part 1 is a standard definition of what is the function of earth wire, okay, which can be commonly found in like most of the books. So this particular B part 1, I won't go through. Okay, so if you have any questions, just let me know. Okay, I will just post the answer maybe in my next video or in the comment below. Okay, if not, I would say this is quite a fair. P1 is actually quite a simple, as a basic question most of the textbook will have. Okay, why fuse is always connected in the live wire instead of neutral wire? Let's run through it. Okay, now why do I want fuse in live wire? It's because when there is a high current, then the fuse rating, okay, so not just higher, it's higher than fuse rating. Okay, so what it does, okay, when it's higher than fuse rating, okay, the fuse will melt. So the appliances will be able to be disconnect from, okay, from the high voltage of the supply, of the power supply. Okay, so by disconnecting the appliances from the high supply, and thus what we do, and we thus, okay, the person touch, okay, keep it simple, no electrocution will occur. Okay, no electrocution will occur. Okay, So the keywords that we are highlighting here is, remember, the function of fuse. Okay, for fuse to activate, you must be higher than the fuse rating. So I need the students to tell me it's higher than fuse rating. Okay, and when it does is that when it does, it will actually melt. Then when it melt, okay, what's the purpose of the fuse melting? It's actually, main aim is actually to disconnect the appliances from the high voltage supply. And so when I disconnect it, it means that there won't be any chance that anybody touches this, no electrocution will occur. And that's why one of the reasons why the fuse is always connected to the live voltage instead, live wire instead of the neutral wire. If I connect it to neutral, right, even with the fuse high voltage, the object is still connected to high voltage, and the current will still flow through or flow out from the high voltage. Okay, so this is one of the things that we always tell students. Okay, where fuse and switch has to be connected to the live wire. Okay, with this will be the end of the paper 2. Okay, paper 2 of this particular prelim paper is a long video. Okay, so same thing as before. I will upload the other video, the paper 1. Okay, if you need the paper 1, you can actually take a look at the next video. I will leave the link down below. Is any questions? Okay, if I make any mistakes or you have any questions, okay, please feel free to leave your comments at the bottom below so that I can get back to you ASAP. Okay, other than that, okay, so remember, okay, click like and subscribe to my channel. Okay, anything, okay, we will see you in the next video. Bye bye.